So my name is Stephen Tove. I'm on the .NET team here at Microsoft, and I do spend a lot of my time thinking, and in some cases once a year, writing about performance. As was alluded to, I've written every year. I end up writing a blog post, which seems to get longer and longer and longer. About the performance improvements in the latest release. And most recently in September, I put out performance improvements in .NET 9. And when I went to just see approximately how long it was, and I went to print it, it was about 300 pieces of paper. So please don't print it. Save the earth, save the trees. But this is just sort of to speak to the magnitude of the number of performance improvements that have found their way into this release. It's also to speak to the fact that there's no way in 40, 45 minutes that I could possibly cover even a fraction of the hundreds of performance improvements that have gone into the release. The blog post covered about 350 of them. So instead, what I've decided to do is narrow it down and focus on a particular sliver, a particular kind of performance improvements. So there's a variety of different kinds of performance improvements that the blog post always covers. There's a large chunk that's basically just upgrade and things get faster. These are improvements to the just-in-time compiler, improvements to the garbage collector, improvements to all of the existing methods and properties and types and so on that you're using in your application. And those improvements, when you upgrade, you end up calling into the new implementations. Your functionality, your application, your service just gets better. There's another class of performance improvement that's around when you recompile the application and you take advantage of performance improvements in terms of what the C# compiler or the F# compiler or the VB compiler or so on are able to generate. You upgrade, you recompile, and you automatically take advantage of all those improvements. And then there's the last class of improvement, which is we expose new APIs focused on performance, such that after you upgrade, after you get that free lunch, after you get that free performance, you can then make small tweaks here and there to your application to take advantage of new functionality that we've exposed to make it even faster. And so what I've decided to do is I've picked out just a handful of APIs. I picked maybe 5 methods to talk about for the next 35, 40 minutes that are some of my favorites in the release. But this is out of dozens of performance-focused APIs and literally thousands of new APIs that exist for a variety of reasons across .NET 9. So with that, let's dive in and focus, I think, on what is probably my favorite new API in all of .NET 9. And it's got this strange looking name, get alternate lookup, but it's actually a set of methods. It exists on multiple of the core collection types: dictionary, concurrent dictionary, frozen dictionary, hash set, frozen set, and so on. And it is a piece of functionality that we were only able to add by making changes across the entire stack. We've made changes to enable this in the runtime. We made changes to enable this in the libraries. We made changes to enable this in the language and the compiler. And it's a piece of functionality that can make a really critical difference on core code paths in your application. So that was a lot about it without saying what it actually is. So let's actually see what it is by diving into some code. So normally, if I was doing benchmarking, I would use benchmark.net. Benchmark.net is a really cool library. You see I use it in my blog posts. And it allows you to get very accurate, very precise measurements for down to the nanosecond level on whatever you want to measure in .NET. But in order to get those very accurate, very precise measurements, it ends up taking quite a lot of time to sort of zero in on the statistically significant information, which doesn't make for a very good demo in a live talk. So instead, I'm falling back on sort of the equivalent of printf debugging. I'm using a stopwatch, and I'm starting it, I'm stopping it, I'm tracking how much memory was allocated, and I'm going to do a little work in the middle. I'm going to do this over and over, and I'm just going to print out each time how long it took and how much it allocated. And the scenario that we're going to be looking at for this is I've downloaded Pride and Prejudice from Project Gutenberg. And we're going to count how many words show up in this document, but not just how many words, how many of each word. So basically building up a frequency table or a histogram. And to do that, we'll use a dictionary. So I'll come in here and I'll say dictionary from string to int, and let's call this frequency. And I'm just going to construct a new one of those. Now, if we're looking for words, that means we're parsing. When I think parsing, I think regular expression. So I want to use a regex. So let me come down here to my little helpers type, and I'm going to use a partial method here called words filled in by the regular expression source generator that we shipped in .NET 7. So you can see words is a little squiggly right now because I've declared a partial method and I haven't provided any implementation for it. But I'm going to let the compiler or the source generator provide that implementation. So I'm going to use a regular expression. I'm going to give it to generated regex, and then at compile time, the source generator is going to generate all the code necessary for this regular expression. Now, the regular expression I want to use is basically parsing out words, and you can see actually Copilot here is suggesting for me exactly what I want, which is a regular expression that looks for any number of positive number of word characters surrounded by word boundaries. And even if I wasn't well versed in regex, I could just hover over this and have the regex source generator tell me in English exactly what this is doing. It's matching at a word boundary, matching a word character atomically at least once, and then matching it at a word boundary again. Great. So I've got my regex. So I'm going to come in here and I'll say for each match, M in helpers.words.matches on text. And then I want to keep track of exactly how many times each word occurred. So I'll just let Copilot write that for me because it's doing exactly what I wanted to do, which was I'm going to try and get the word that I found from the dictionary. If it existed, I'm going to get its count. I'm going to store the count back into the dictionary. And if it didn't, I'm just going to set that to 1. And I'm just going to clean this up a little bit just from a stylistic perspective. I actually would generally write it more like this. Again, I'll let Copilot finish that for me. So I'm looking to see if the word exists. If it does, I'm storing the new result back in. If not, I'm initializing it to 1. Great. I can run this. So let me save that. Let me switch over to the console. I'll say .NET run C release. And we can see it's taking to do this, I think it was about 10 iterations. It's taking about a little over a second, and we're allocating about 340, 350 megabytes. That's a lot just to do word counting. So how can we make this better? Well, again, we're not even to .NET 9 yet. In .NET 7, we actually introduced a new version of matches, one called enumerate matches. I'm just going to change this to var. That is an amortized allocation-free version of matches. And it does that by only having to return the index and the length of each match rather than lots of details around things like capture groups. Now, there isn't actually a value on it, but I can just say text.substring with m.index and m.length. Exact same functionality, exact same behavior. But now when I run this, previously we were taking about a second and 350 megabytes, and we can already see we've dropped down to about 170 milliseconds, and we've gone way down in allocation to 43 megabytes. But where is that 43 megabytes coming from? Well, it's coming from the fact that I'm still allocating a new string for every single time I encounter a word. But is that really necessary? I mean, Pride and Prejudice, I think I counted, it has something like 4,000 occurrences of the word the. I only need to store it into the dictionary once. That's the only time I really need the as a string. For the other 3,999 times, I don't really need that string instance. I just need some way to do a comparison with the text against what's in the dictionary. What I'd really like to do is be able to just change this substring to as span, so that I can just get a read-only span of char around the particular region of the text and use that to index into the dictionary. But as you can see, now I'm getting squiggles because I have a dictionary of string and I can't do lookups with a read-only span of char into a dictionary of string, or at least I couldn't until .NET 9. So this is what get alternate lookup provides. So let me come back up here. I'm going to create a new local. I'll call this lookup. And I'm going to say frequency get alternate lookup. And I'm going to pass in a read-only span of char. Now, I mentioned that this feature required changes across runtime, libraries, and language. You'll notice this read-only span char here as a generic method parameter. You could not write that before C# 13 or .NET 9. You couldn't use spans or really any ref struct as a generic parameter. Now you can. There's a new feature in .NET 9 and C# 13 called allows ref struct that allows you to specify that a generic parameter can actually be a ref struct. And this then causes the compiler to validate the implementation of the method to ensure that you're not doing anything with the type parameter that you couldn't do with a ref struct. And then at the call site, it allows you to use a ref struct in the method. So I'm doing that here. Now with this lookup, I can just take this and I'll copy that. I'll replace frequency with lookup, and now everything compiles. The squiggles go away because I'm allowed to do a try get value on this alternate lookup with the alternate lookup key of a read-only span. Now, when I run this, I didn't actually want to build that. Well, it's fine. Go back over here. I'll run it here just so we can see the history a little bit. And now we can see that we're about the same speed as we were, but we're at 0 megabytes allocated because we're doing this, we're just slicing, and the only time it would ever need to allocate is when initially storing into the dictionary. So how does all this work? Well, there is a new interface in .NET 9 called iAlternate Equality Compare, and I can create an iAlternate Equality Compare between the two things that I want to compare. In this case, a read-only span of char and a string. What can I do with this? Well, if you look, we can see there's an equals method. This equals method takes a read-only span of char and a string. So it's comparing not just string to string, but read-only span char to string, or really whatever was in this position. Similarly, just like on iEquality compare, there's a getHashCode method, which takes a not string, but read-only span of char. So it looks exactly like iEquality compare so far. But then there's one more method that's critical to the scenario we just looked at, and that's a method called create, which maps between the alternate key and the original key. So we can pass in a read-only span of char, and we get back a string. And this is critical because that first time when I go to store this value into the dictionary, I'm giving it a read-only span of char, but it needs to be able to store it as a string key. So it needs to be able to call to that comparer's create method to convert the read-only span char into a string. Why is this relevant? How does this show up? Well, I mentioned that I could pass read-only span char here. I can actually pass anything here. The critical piece is that the comparer that's being used by the dictionary needs to implement iAlternate Equality Compare of whatever is here to whatever is here. So when I create this dictionary and I say new dictionary, and I pass in some string comparer like string comparer ordinal ignored case, this comparer needs to implement the relevant interface. If I wanted to pass in here a Steve's cool type, all I need to ensure is that whatever comparer I pass here implements iAlternate Equality Compare from Steve's cool type to string. And as it turns out, in .NET 9, all of the instances you can get from string compare.ordinal ignore case, string compare.invariant culture ignore case, string compare.ordinal current culture, they all implement support for comparing read-only span of char with string, as does the default compare that you get back from equality compare string.default. So any of these just work, and that's why when I initialized my dictionary with to be an empty dictionary, and it's using that default compare, everything here just worked, which is pretty cool. So this is a really cool way to avoid allocation on what are often hot paths where you're doing lots and lots and lots of dictionary lookups. This works with dictionary, concurrent dictionary, frozen dictionary, hash set, frozen hash set, a frozen set. It is a really cool and powerful piece of functionality, which is why it is probably my favorite API in all of .NET. All right. So next up, and we're going to continue our example by using a few other APIs. If you've written any .NET code pretty much ever in the last 20 years, you've probably used string.split. It is a ubiquitous method that's super handy for giving one or more separators as a char or as a string, and then having it give you back an array of all the things that came between those separators. So if I had the string the space performance, and I gave it a separator of space, I'm going to get back an array of two elements, the and performance. Unfortunately, while it is ubiquitous and is used everywhere, it's not exactly the highest performing method. We try and make it as fast as we can, but it has to allocate a string array to hold all the results, and it has to allocate a new string for every single element in that array. It would be nice if there were alternatives that provided allocation-free versions. And in .NET 9, you get that. In fact, you get that in two different ways for both char and string separators or separators of type T, and then also for regular expressions, because regex also has a split method where instead of giving it a char or a string as the separator, you can give it a regular expression such that any match becomes the separator. And in .NET 9, there are now ways to do this allocation-free and on spans, not just on strings. So let's take a look at that in our previous example. So previously, I was using this regular expression to match words. Instead, I'm going to change this to sort of invert it. I'm going to look for white space instead, and that means coming up here and changing my regular expression pattern, and I'll just use a regular expression that matches a white space character atomically at least once. And then up here, instead of matching words, I'm going to split on white space. So to do that, I'll use split. Now this split method returns an array of strings. So I'm getting back strings here. So for now, for simplicity, I'm just going to say that the word is that value, and I can run this. That'll work fine. So let me switch over to my console, run this again. We can see we're back up to a higher value. We're using regex, and we're getting back a string array. We can see we're allocating about 73 megabytes. So let me switch back over here, and instead of using split, I will use the new enumerate splits method from .NET 9. Now, instead of getting back a string, now we're getting back a range. What can I do with that range? Well, I can do something like text using the indexer to get back a string. Right? So I can run this. Let me save that. Switch over here. Now we can see we're about twice as fast, and we're back down to about the same amount of allocation that we saw before we switched to spans, because every single time I do this indexing here, I am allocating a new string. But I can avoid that just by saying as span with my range. In fact, let me just call this range to make that clear. Switch back over here. Now we see we're taking a little bit faster, but we're again down to 0 megabytes allocated. We're not allocating anything because we're just using spans to index over this original text. I showed doing this with regular expressions, but I mentioned you can do this just with strings as well. Let me just come back up here and I'll say text as span, so I can operate over a span. And I'll just do split with a space. So not exactly the same search because I'm just splitting on a single space. But notice this still compiles because this split is giving me back an enumerator of ranges. And I can run that again. And now because we're not paying for the more complex regex, we've shaved a lot more time off it as well. And we're still down at 0 megabytes allocated, which is really cool. Now, I mentioned the other, we're seeing some new APIs. We're seeing APIs that showed up in previous releases. There's one more fun little trick that I can use here to make this go even faster. You can see here, whether I'm using dictionary directly or lookup, I'm actually doing 2 dictionary lookups on each operation. I'm checking to see what the current value was, or if there was a current value. Then I compute the new value, and I have to do another lookup in the dictionary to store this new value back into it. What if there were a way for me to just do this with one lookup? And in fact, there is. There is this little known type called collections Marshall, and it's off on the side because it represents things that are a little bit less safe for one reason or another. In this particular case, there's a method called getValueRef or addDefault, and I can pass in here my lookup, the thing I'm looking up. This last parameter just says whether it exists or not, and it returns a reference to the location of the value in the dictionary. And that way I can just directly increment that value. Now, I mentioned this collection Marshall type is for slightly less safe things. This is a memory safe operation. However, if after getting the reference back here, I were to then mutate the dictionary in a way that would grow the dictionary and cause it to sort of throw away the arrays that it was using under the cover, the reference that I have would be to one of those arrays that isn't actually going to be used anymore. So my changes wouldn't actually show up in the dictionary. And that's why it's sort of off to the side. But regardless, this is now the exact same piece of functionality. And if I use this and I run it, now instead of taking, say, 100 milliseconds, we're still allocating 0 megabytes, but I've shaved another basically third off the cost of this operation just by doing these little tweaks to my code, which is pretty darn cool. All right. So those are a few of my favorite APIs. Move on to the next one. In .NET 8, when I wrote the blog post about .NET 8, I cited two features as my favorite features in the release. The first was the turning on of dynamic PGO by default, because that helps every single .NET application out there by kind of imbuing the JIT with superpowers to be able to generate code specialized to the code that's to what's happening in the application at execution time, profiling it and then generating new code based on that. Super critical piece of functionality, and it gets even better in .NET 9. But I called that a second feature. That was probably my second favorite feature in all of .NET 8, and that was a new type called search values. Search values allows you to do searches, index of any except kind of searches. But you get to give it ahead of time all of the things you might want to be searching for. And by doing it ahead of time, you allow the system to spend more time figuring out how to optimize for that particular set of data, such that when you later use it, it's got all the stuff pre-computed to be able to do it as quickly as possible. And it's not just one algorithm that it's pre-computing data for. It's able to look at the data and say, okay, I know that for this set of data you're searching for, algorithm A is going to be better, or algorithm B is going to be better, or algorithm C is going to be better. And it can pre-compute the data relevant to that algorithm. And then again, when you go to do your index of any, everything is just faster. So we ship search values in .NET 8, and specifically for bytes and chars. And we end up using it in, I think, in .NET 8 in probably 50 or 60 places across the core libraries for really critical operations. So for example, when validating that an HTTP header in either HTTP client or in ASP.NET doesn't contain any invalid data, we'll have a search values of byte or a search values of char that we can use to cache all of the search set for everything that's considered valid or everything that's considered invalid, thus making the later searches really, really fast. So search values of byte allowed you to search for any set of bytes within an array of bytes, a span of bytes. Search values of char allowed you to search for any set of chars within a string or a span, or anything from which you can get a read-only span of char. In .NET 9, we introduced the ability to use search values of T with string. Now, excuse me, this isn't searching for a set of strings within a larger set of strings. So it's not, I have an array of strings and I'm searching for a few strings within that. Rather, this is searching for a set of strings within a string or within a span. So it's basically multi-substring search. So for example, if I wanted to search Pride and Prejudice for the days of the week, I could create a search values of string for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then I can say index of any to do a search. So let's actually look at that. So let's say we can get rid of my dictionary here. We're not going to be using that anymore. Let's say that I had a string array, days of the week. Let Copilot finish that for me. Thank you very much. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And I want to create a count of all the time that these words occur in my Pride and Prejudice text. Now, for a long time, we've had a method like index of, where I could specify Monday, and I could do, say, an ordinal ignore case search for Monday. But there was no API that allowed me to do index of any and pass in here days of week. That just didn't exist. And you can see I'm getting squigglies. And part of the reason that doesn't exist is this is a very expensive operation to do without doing any kind of pre-computation. And in fact, we can see how expensive it is by just implementing it ourselves. So let's say we're going to iterate from I through text.length. And then at each position in text, we're going to see if that text location starts with one of these days of the week. So we'll say for each day of week in days of week, if, yeah, there we go. If the text at this position starts with the day of the week, we'll increment our count. And I'll just, that was actually right what it was doing, but just for simplicity, I'm just going to break out of the loop and not have to worry about dealing with fixing up this incrementing position here. So this isn't 100% as optimal as it could be. Really, I would want to jump to the end of the string that I just matched, but this will be fine. And the count that's produced will be accurate because none of these strings acts as a prefix for any of the others. So I can run this. Let's go back over to, oh, actually, let me just do one more thing. I have this little helper method here called use that's no inlining. And I do that just to guarantee that the JIT can't see, well, you're never using count, so therefore I can just eliminate this whole operation because you're never actually using the computed results. So let me switch back to console here, and we'll run this. And we can see that this operation is, we're not allocating anything, but we're taking about 220, 230 milliseconds to do this operation. Because for every character in the input text, I'm checking to see whether the day of the week exists at that position. Now, there might be certain things I could do. Maybe I could try and say, invert this, for each day of week, do an index of on the original text. But that's not ideal either, because then if, let's say, Sunday was the only word that occurred in the original text, I'm going to have to search the whole text 6 full times before I get to something that might discover it. What I really want to do is be able to efficiently search for all of these at the same time using a built-in API that takes advantage of everything the hardware has to offer in terms of things like SIMD, vectorized processing, where I can process multiple elements, multiple pieces of data at the same time. So let's rewrite this. Let's come back up here. We'll still have our count, but instead of looping through it, I'm going to create a read-only span of char that I initialize to the remaining text. And then I'll say, while there's still anything remaining, while it's not empty, it sees that I have a regex and it's trying to use it, but I don't actually want to for this purpose, so we'll write it ourselves. I want to do a search here. Well, I'm going to say remaining index of any using, and what am I going to pass here? Well, I'm going to create a search values of string. We'll call this days of the week search values, and we'll do search values dot create with days of week and string comparison ordinal ignore case. So we've got our days of week search values here, and then I just pass that to index of n, right? Now I can say, if I didn't find anything, I'm going to break out of the loop. If I did, we'll increment count, and then we're going to need to slice remaining to, again, just as I did last time, we're kind of incrementing by 1. Here, we're not worrying about jumping to the end of the word. We'll just move 1 past where we matched. So we've got our implementation here. Switch back over to my code. It was taking about 230 milliseconds to run. Now when I run it using search values, you can see it's scrolling super fast. We're just taking a little over 1 millisecond. So I don't know what that is, a 200-fold or somewhere close to that improvement in throughput by taking advantage of this functionality. Now you saw that Copilot kept trying to push me to use regex. So let's use regex. You might be using search values directly, but anytime we expose new functionality, new APIs in the core libraries, we really like to then use that new performance improving functionality everywhere else higher in the stack that we can, because then when you're using that higher level functionality, you automatically get the benefits of the lower level improvements as well. And that shows up here as well with regular expression. Obviously, regex is all about searching. So let's say I wanted to change this, and I wanted this to be days of week. So I can do that, and then I'll come up here, and I'll say Monday, Tuesday, Wednesday, Thursday, Friday, and it's, again, Copilot nicely completes that for me. One other little nicety here, if you are familiar with using the regex source generator, in previous releases, you could only do methods. Now with C#13, it's the language supports partial properties, and so does the regex source generator. So I can get a slightly nicer syntax here and just use property. So now that I've got my regex here, I can come up and I can do this whole operation just by saying helpers.daysofweek.count. And this works with strings. This works with spans. In fact, I could say as span, and it compiles just fine because count has overloads that work with span. I can run this. We can see it's taking about the same amount of time. I didn't have to write all that complicated code. How is it taking the same amount of time? Well, it's using search values of string under the covers. If we go in here and we go to definition, we can actually see the implementation that has been generated for me live by the source generator. And if I scroll down to the code that is responsible for finding the next position in the input at which to possibly do a match, we can see, sure enough, it's calling index of any, passing something in. What is it passing in? It's passing in a search values of string that it's created using the days of the week and ordinal ignore case. You might notice if you're eagle-eyed that it doesn't have a letter at the end here. That's not a bug. That's by design. There's some optimizations happening in regex that's just trying to keep these under a certain length. But that's fine because after it does this match, it's actually going to, after it does this find, it's actually going to do a full match at that location. So we're able to use this underlying functionality directly. We're able to use it implicitly as part of using regex. It is a very powerful, efficient mechanism. And as I mentioned before, just as like for search values of byte and search values of char, there are a plethora of different implementations that the search values.create will select based on the inputs and decide what information to gather, what to pre-compute, such that when we actually do the search, it is as fast as possible. All right. So that was search values of string. Let's look at one more. And one more, but really this is hundreds more. And that is a type called tensor primitives. So in .NET 8, we introduced a new library called System Numerics Tensors that contained basically one type. In .NET 9, it contains a whole lot more, and you should absolutely go check that out. But for the purposes of this talk, it contained tensor primitives. And tensor primitives had on it about 40 methods, 40 overloads that manipulated collections of floats. Basically, a whole bunch of APIs for doing math, not just on one floating point value, but on a span of floating point values. So for example, tensor primitives.add would take 3 spans, 2 input spans and a destination spans, and it would go pairwise through the inputs, adding the elements from each span and storing it into the destination span. Or tensor primitives.product, which accepted a single span, read-only span of float, and multiplied all the floating point elements and produced a single floating point result. Super useful, super helpful, a lot of great functionality, but it was limited in a couple key ways. First, it had a lot of operations, but it didn't have all the operations. If you look at math and mathf, there are probably 100 different operations that show up there. If you look at the generic math interfaces that were introduced in .NET 7, there's 100 different, around 100 different operations that are exposed. Tensor primitives only exposed a fraction of what was there. The second limitation was it was only for float. It wasn't for double, it wasn't for half, it wasn't for int or long or anything that implemented those generic math interfaces. So in .NET 9, both of those have been rectified. Tensor primitives now contains effectively the full surface area of everything you would see on math and mathf, as well as on the generic math interfaces, and it contains them as generic methods rather than just for floating point. So we can actually see that. Let me just delete some stuff here. We don't need any of this anymore. And if I come in here and I type tensor primitives and I dot, I can scroll for quite a while looking through all of the various APIs that show up on tensor primitives. And many of these are actually multiple overloads for doing things in different ways. So it's not just one, but if I look at add, we can see add has 2 different overloads for doing things in 2 different variants. All told, in .NET 9, tensor primitives has something like 250 overloads on it. Just a huge amount of functionality for doing really interesting things. And as I'm scrolling through, you'll notice that some of these methods have angle brackets after them because they are generic. So if I look at add, there's an overload for add that is specific to float, but there's also an overload of add that takes a T, and it operates on anything that implements the relevant interface. So there's an interface that basically says, I support addition operators. Well, you can use tensor primitives.add with any T that has that. And so it works with pretty much all of the primitive types out of the box. And if you want to bring your own, it works with that too. And wherever possible, these methods are all vectorized to make them super efficient. So let's take a simple example of that. One of the methods that exists on tensor primitives is a method called Hamming distance. There's actually two variants of this. We have Hamming distance and Hamming bit distance. Hamming distance is a complicated name to describe what's basically given two inputs, find the number of locations where they differ. So if I provide the list 1, 2, 3 and the list 1, 2, 4, the Hamming distance between them is 1 because they differed at that last position. If I provide the lists 1, 2, 3 and 4, 5, 6, the Hamming distance is 3 because all the positions differ. Here, Hamming bit distance is instead doing it based on individual bits that differ, whereas Hamming bit distance is on the number of T's that differ. So let's actually just implement our own simple Hamming distance ourselves. So let me say Hamming distance, and let's just do this on 2 read-only spans of bytes. So let's say bytes 1, read-only span, bytes 2. And now let's try to do bit distance. Let me help it fix that. There we go. So now we've implemented Hamming distance. We start the distance at 0. We loop through all the elements. We should probably do a length check here to make sure these are the same length, but I'm ignoring that for now. And anywhere that they differ, we're increasing the distance. So we can try and use this. Let me come up here. This is a pretty fast operation, so I'm gonna increase the number of trials here to something that makes this take a little bit more time. Let me create a few byte arrays up here. Let's do byte 1024. We'll do bytes 2, 1024, and then I'm going to fill this with random data. So I'll say random shared next bytes with bytes 1 and random shared next bytes with bytes 2. And then here I can do distance equals Hamming distance, bytes 1, byte 2, and I'll do my helpers.use with the distance. Right? So I can run that. And we can see doing this, it's a pretty fast operation. Doing this 100,000 times, we're taking about 80 milliseconds to accomplish this task. But I can come up here, and instead of using the Hamming distance that I just wrote, I can use tensor primitives.Hamming distance. It all compiles. We can see this is using the generic overload of Hamming distance that operates on bytes. Now if I run this, not taking 80 milliseconds, but instead taking 2 milliseconds. So I'm on a machine that has AVX 256. So the tensor primitives implementation is lighting up with that, and it's taking advantage of these vectorized operations that allow me to compare many bytes at the same time. If I was on a machine that had 128-bit vectors or 512-bit vectors, tensor primitives is going to scale to whatever the system has and allow that to be operated super efficiently. And that happens for pretty much any of the operations on here. There are a few still left to be vectorized, but for the most part in .NET 9, out of the box, you get great performance using these APIs, which is why they are on my list as being some of my favorite in the whole release. So with that, I am out of time. We can take a few questions, I think, if there are any, but if you haven't read it, the thing I would encourage you to do is to go to the Performance Improvements in .NET 9 blog post. You can read about these APIs and many more, and thousands more performance improvements, or hundreds more performance improvements in the release. And with that, I'll say thank you.